There is definitely a lot of noise, a lot of hype, bullshit, if I can say the word here. A lot of smoke and mirrors, and that is normal when you start getting companies going public, right? And they need to tell something to their investors. And I didn't mention trapped ions before, by the way, with IonQ as well, or Quantinuum working on that side. So trapped ions also a great technology, but I'm a little bit on the fans with Sabine's comments, and she's more the skeptical, and there's many skeptics in the industry, which is fantastic. I think we need all those positions because what we have is a tug of war between some companies or certain companies overselling the capabilities of what's possible today, and then scientists being extremely conservative. And you need to be somewhere in the middle, right? Conservative scientists are great and we need them, and we need to follow the scientific method to be rooted in what's real. But at the same time, we need to be able to dream.
Welcome to a new episode of Engines of Creation. I'm your host, Cristian Mastrodonato. At Engines of Creation, we had CEOs, CTOs, Chief Innovation Officers, professors, but many podcasts can say that. But not many podcasts can say to have a pirate as a guest. And not any pirate, a quantum pirate. In fact, in this insightful episode, we welcome back Sergio Gago, a leading voice in the quantum computing realm. This time, Sergio dives deep into the complexities of quantum computing, expanding on themes from his previous appearance that captivated our listeners and they wanted to hear more. With years of experience in the field, he unpacks the current landscape of quantum technologies, from superconducting qubits to neutral atoms, and discusses the challenges and breakthroughs in hardware development. The discussion also touches on the algorithms that are central to quantum computing and the skepticism surrounding their current applicability compared to classical computing solutions. Sergio shares his perspective on the future of quantum algorithms, highlighting the niche problems that quantum computers are best suited to solve and the potential for industry-specific applications. As we explore the intersection of quantum computing and cybersecurity, Sergio outlines the ongoing efforts in post-quantum cryptography and the importance of preparing for the implication of quantum advancements on encryption methods. Join us for a thought-provoking conversation that demystifies quantum computing and inspires a new generation of thinkers and innovators in this realm of technology. Please don't forget to follow Engines of Creation and leave us a rating and a review. And don't hesitate to share this episode on social media and with friends and colleagues who might be interested. This podcast counts on you to grow and help other people to understand and embrace complexity, to innovate and create. And now, let's go! Welcome everyone to Engines of Creation. And for the first time, we have a guest coming for the second time. And I am very, very happy to have Sergio Gago again with us today, but this time talking about quantum computing. Last time we just touched a little bit about that, and a lot of listeners came back saying, we want to know more. You never talk about quantum computing. And so, well, here we are. And also that's particularly helpful because Sergio not only has spent a lot of time quantum computing over the last years, but he also owns a Substack, Quantum Pirate. So I think no one can guide us through the complexities of the quantum industry nowadays. So welcome, Sergio. I'm going to point to the listeners that didn't listen to the previous episode to have a sort of more detailed introduction about you. But how did you get into quantum? Why is it so exciting for you?
Awesome. Well, first of all, thank you very much, Christian, for the honor of being twice in your podcast, not once, but twice. It is always tricky because when we talk about data or AI or anything else, there's always this kind of leeway into quantum, and I try to pull myself and not spend too much on that. So I'm super happy that I could come back and then talk 100% about quantum today, which is one of my passions. Um, so Yeah, I think as you said, we talked at length about my intro and all that in your previous the previous time I was here. Um, so piggy a little bit of piggyback on that. I spent most of my life either as a CTO dealing in big data companies, AI companies, and the like, or digital companies. And at some point, about it's going to be maybe 8 years ago or something like that, I realized, hey, the machine learning world, what we call today the classical machine learning world, it's kind of stagnated. Right? We're doing a lot of good stuff, sure, but the models, the development, and all that is always kind of the same. You have to curate your data, normalize it, spend a lot of time on that, build a platform, MLOps, all those nice things, data fabric, and then run inference on that. But what's next? It seemed like there was not a lot of next things. Sure, computer vision, robotics, but all that was very far away. So I decided let's do something different, and I decided to enroll in a master's in biocomputing. Of all things, and I was in that program, and I realized two things. Right, we were doing this exercise. We were trying to analyze doing pattern recognition on a genome string. And I realized two things. In biocomputing, the smart people in the room are the biologists. The computer scientists were the lab assistants trying to do pattern recognition and regex and all that stuff, right? Doing the computing stuff, which is interesting, right? But we're not the first ones named in the paper publishing the Nobel Prize or something. Nevertheless, it was super interesting to know more about how a virus would attach to a given protein and whatnot. But I remember very closely one lesson, one session where the professor said, "Look, as you know, this is an NP hard problem." Identifying this part of the genome, the GTAC elements. So that's a problem that grows exponentially with the size of the problem, meaning you cannot recognize the whole pattern, the whole genome in a compute time. So you can only do heuristics. However, there's this company that is building or has built a quantum computer, and maybe they can help solve this problem better and faster. And the world stopped for me in that moment. I was like, hold on. What do you mean? I remember Richard Feynman's dreams of quantum computers and people working on that, but all that was just math and experiments. There's no quantum computers. And oh boy, how wrong I was. That once I started pulling the string from that, I realized that there was IBM had computers that just were released on the cloud. D-Wave was already putting their computer as well out there. So it was like, okay, we found something really interesting. I dropped the master's on biocomputing and immediately went into the rabbit hole of quantum computers, always from the perspective of my safe bet, which is an engineering one. I am not a physicist. I'm not a PhD in physics or anything like that. So I always tackled it from the perspective of a machine learning specialist, if you will, and an engineer. And I think that gave me a unique perspective on how quantum algorithms work and how we deal with these machines. How do we bring in this pipeline? And ever since that's the whole story I've been creating in quantum and how I went very deep into that, built a couple of companies in quantum, created, as you mentioned, the one of the widest distributed newsletters in quantum in the world, the Quantum Pirates, and build the quantum teams in a couple of large companies. I did a master's in quantum information as well, so I could talk with some knowledge of what I'm doing. Did the actual coding myself, visited many companies, many hardware companies, presented at many conferences, and then generative AI came and they pulled me back into the world of artificial intelligence. And what I'm trying to do now is juggle between those two worlds, right? The artificial intelligence and machine learning and data, which is what I do at Cloudera, and also the quantum world, which is what I do actively either as an investor or advisor or in my newsletter and so on.
Well, maybe you were wrong after all. AI had still something to say or give you with generative AI. But I do agree that quantum is still a super fascinating topic. And as you know, we definitely share this passion. So I would think many of the listeners of this podcast heard about quantum computing in the past, maybe because I mentioned it or just because sort of it's it's becoming kind of a more and more mainstream, and is growing. But I think it would be helpful if you could navigate us a little bit on what are the main technologies around quantum computing. I think historically we started from superconducting qubits, but actually now there are different technologies, but also around the algorithms and where is the potential and what are the main algorithms for industrial application. So let's look first possibly at the hardware and then what we're trying to build. So is it superconducting qubits still the biggest thing, and I might start asking you what is a qubit first of all, and how they can manage
Yeah.
to work with a qubit actually.
That's a good point, and we can probably start from there. Over the years, I learned that the best way to start talking about quantum is not to bring superposition and entanglement and interference and all the quantum mechanics concepts, because then that's when people close the podcast and go and do something else, ideally alcohol involved or something. Because again, quantum mechanics are extremely difficult to understand. It's part of its ether of sorts. So maybe a simpler way to think about quantum computers is that it is a different type of architecture to compute. It's closer to HPC or to supercomputers. It's closer to that type of devices, not to your laptop, that are made so that certain types of mathematical problems, and I want to emphasize that certain types can be done better and faster than today. Right? And we have first to identify which of those problems are better suited for a quantum computer. For example, running Excel or running a video game can be done perfectly fine on your laptop, can be done perfectly fine with a GPU and the things that we have today. Creating a machine learning algorithm that identifies spam on your inbox, that's a perfectly well solved problem that we do with machine learning today. So we need to aim for other types of, I'm going to say, niche mathematical problems that are still extremely important for humankind to solve, whether it is protein folding, identifying virus chains and vectors on the viruses, financial markets and its evaluation. There are many, many problems, typically combinatorial problems, effectively when you have to combine many things and find the right solution for that, or simulation problems for the quants in the room, Monte Carlo simulations, for example. How do you model and simulate markets or molecules moving in vacuum? Any of those things can be solved with the same mathematical construct. So we have many of those mathematical problems in the world. For example, how your courier tries to plot the route in your city to drop your parcel quicker and better at your house, together with the other 50 parcels that this person needs to deploy. That is a route optimization problem that, again, is really complex to find. We call this NP and NP hard problems. And the better way to imagine this is something that we all do or know how to do, a Sudoku, for example. So, your Sudoku on the newspaper, you have all those numbers and you know the rules. They have to be a different number and the rows and the columns and then in the little boxes. If I give you a normal newspaper Sudoku with normal difficulty, it would take any of us as a human, maybe a minute or 5 minutes, you name it, depending on how good we are at this type of thing. A computer would take less than a second to solve that Sudoku. Now, if I give you a 40 by 40 Sudoku, right, a massive square with 40 numbers, 40 rows, and 40 columns, that would take a massive amount of time for a computer. It would be absolutely impossible for us as humans. It does not grow linearly as the problem of the size grows, but grows exponentially or even more in a factorial. The same happens when you try to run a combinatorial problem. For example, you have all these many stocks in the market, whether it is NASDAQ or Dow Jones and so on, and you want to create the perfect investment portfolio. There are almost infinite combinations on how do you want to distribute your stock picks into that. And an almost same amount of infinite variables and constraints that you want to put in.
Free audio post-production by alphonic.com.